This time we have the same function as in the previous exercise. And again, we want to calculate the Laurent series, but this time we're going to do this in the outer ring and not in the inner ring, where the modulus of z is bigger than 1. So pause the video and try to figure out how to calculate the Laurent series. First of all, you might wonder, if you go back to the previous exercise in the inner ring, which part breaks down? Well, the issue there is that we used series expansion for 1 over 1 minus z. Now the problem is that this guy here becomes divergent if the modulus of z is bigger than 1. So we cannot use that. So this is the problematic point here. However, you soon realize that if the modulus of z is bigger than 1, then the modulus of 1 over z is smaller than 1. So this could be a way out of our problem here. And indeed, let's rewrite our function f of z, which is exponential z minus 1. And let's bring out z here so that we have for our second factor 1 over 1 minus z. And now we're back in business because we have something that looks very similar here. We have something that in magnitude is smaller than 1, so we can just apply the same series expansion. This time not using z, but using 1 over z. So we can write this as our 1 over z, and then we have the series expansion for the exponential, m going from 0 to infinity, z to the power of m divided by m factorial. And then we have our second series expansion where we have a summation for m going from 0 to infinity. And at this point, hopefully, I hear a huge uproar in the audience because I'm using here the same summation index, which is of course not done if you use the product of two series expansions. So you should definitely use a different summation index here. Otherwise, you will get into trouble, mainly with me. Okay, so using n there, then we can continue writing that this is 1 over z to the power of n. Okay, that's good. But what we now would like to do is we would like to collect all of the coefficients that belong to the same power of z. So for example, z to the power of k. So pause the video, rearrange this stuff so that you can explicitly write down what's the coefficient of a certain power of z is. So where does the z appear everywhere? Well, in basically 3 places, here, here, and here. So the first one will just give us an exponent minus 1. Second one an exponent m, the third one an exponent minus n. And we're going to combine those into a new summation index k, which will now also mean that m and n are no longer independent, but are rather coupled to our new summation index k. And we need to figure out how to rearrange all of the terms in that product here so that we can get some order in the chaos. Now you might remember that we use this diagram here where we have values of m and values of n, and each dot in this diagram basically corresponds to a term in the product of these two series expansions. And we should make sure that we don't forget any of these dots. But now we're going to order these dots in such a way that we make use of the summation index k. So let's have a look where we find certain values of k. Let's first focus on the diagonal over here, where m and n are equal. So if m and n are equal, that means that k is equal to minus 1. So k is equal to minus 1 on the diagonal. Down here, we have m equal to 1 and n equal to 0. So this means here that k will be equal to 0. So along this line, we have k equal to 0. And along that line, for example, we have k equal to minus 2. So let's just double check that we have, for example, a point here where m is equal to 1 and n is equal to 2. So then indeed, if we plug that into that formula, we get k is equal to minus 2. So this time we arrange it along diagonal lines along this 45-degree angle here. It also becomes obvious that if we want to make sure that we do not forget any point, k basically needs to run all the way from minus infinity up there to plus infinity down here. So our summation will run from minus infinity to plus infinity. Next point of order is that if we're at a certain value of k, so let's say we're on one of these lines here, what are then the bounds for m, for example? Now in this case, it's a bit different depending on whether you're in this situation down here or in that situation up here. Because if we're looking, for example, at this line over here, where k is equal to -1, or also for lower values of k, it turns out that the smallest value of m that you need to take into account is always on this line here. So the smallest value is always equal to 0. So as soon as k is smaller than or equal to -1, our summation for m starts at 0 and runs all the way towards infinity. But it's different when k is actually bigger than 1. So for example, in the case where k, bigger than minus 1. So in the case where k is equal to 0, for example, you see that m starts here. So it no longer starts at 0, but it starts at 1. Okay, so for k equal to 0, it starts at 1. For k equal to 1, you see in this diagram that it starts at 2. So in general, m will run from k plus 1 to infinity. So this is a rather complicated lower bound here, depending on the exact value of k. But this is how we should rearrange stuff and recollect them based on insights from that diagram. By the way, I also told you that there's a different way based on algebra where you can get some hints on these different bounds here. But I also told you that this not always gives you the full picture. But let's now illustrate that trick, that algebraic trick here. The trick is basically to use that relationship between our different summation indices and extract the index that we no longer use in this case. So in this case, that's n. So if we calculate n from that expression, we get that n is equal to -1 plus m minus k. And we know that n starts at 0, so this value is bigger than or equal to 0. Now, if you do that, you gain the information that m is basically bigger than or equal to k plus 1. Which is what we found here for this particular case, but it's not completely accurate because it brushes over this particular case here. So bear in mind that with this algebraic trick, we don't always get the full picture, and this is an example here. Okay, the hard work seems done now. We have rearranged stuff. We know what the different bounds are. So finally, we can write down that our function here, f of z, can be written as a Laurent series for values of k that will run from -infinity to plus infinity. And then for each value of k, we will have a sum for m running from this complicated lower bound here, which I do not have space to copy, to infinity. And then if we go back, what are the coefficients? We just look at this thing over here. So the coefficients are just the inverse factorials of m. So let's go back here and write 1 over m factorial z to the power of k. So the good news is that now we have an explicit form for the coefficient of z to the power of k. The bad news is that it has this very complicated lower bound, which is basically this if then else statement here. So wouldn't it be nice if we sort of found a way to compress this and make this a little bit more aesthetically pleasing? Wouldn't it be nice if we were able to write down as a lower bound here k plus 1, just as this algebraic trick suggested? Now, if we do that, then basically we're cheating a little bit, especially for the cases up here where k is smaller than -1. Because in that case, so for negative values of k, so let's say that k is equal to -1 here. If we start then at k plus 1, so actually we should use -2 as an example. So say we have k equal to -2 here. Then if we change our bound not to start at 0, but to start at k plus 1, then we should start at -2 plus 1, and we should basically start at, we should basically also include that guy over here, starting at -1. And likewise, for that line over here, we should also include these terms. The problem is, of course, if we change our lower bound, we add these ghost terms, which are not really there in our original product of the series expansion. So it seems that that's a very bad idea because we introduce extra terms. But let's take a look at the coefficients of these extra terms. So they all involve negative values of m. And then it's a bit strange to try and think about negative factorials here. Now, luckily, thanks to our friend Euler and his gamma function, there is a generalization of factorials, for example, also to negative integers. And that generalization basically tells you that if you have negative factorials, that in magnitude, these guys will always be infinity. So if L is equal to plus or minus 1 or plus or minus 2, so all of these, sorry, if L is equal to 1, 2, or 3, so all of these negative factorials will either be plus or minus infinity, which means that if you look at 1 over these factorials, that they will all be 0. So the good news is we can safely reintroduce these ghost factors here to simplify our lower bound, simply because of the fact that the extra terms that we add are 0 anyhow. So that's a rather complicated explanation, just to say that it's okay in this case to use this much simpler lower bound. And we do have a nice, aesthetically pleasing formula.